Hello there, this is Anton Duplessis, and I'm going to show you in this video how to make analysis of battery cells in Dragonfly software. The idea here is to show you that it's possible to do manual measurements easily, how to do typical inspection of a cylindrical battery cell, and to show you also some automation tools with deep learning. So practically how to train your own model to do that. So let me get started with a screen share, and I've got some data loaded up already in Dragonfly 2024.1. As you see in the 3D view, it's a top of a cylindrical cell, which is visualizing most of the dense material by default here. So, and then we have a quad view, so you have cross-sectional views, slices also visualized. If your Dragonfly doesn't open up data like this, you might have to go down on the left to the layout panel to change from the single 2D view to the quad view like this. And when you have a quad view, you can anytime maximize and minimize a particular view. Like if I double click in this view, you see this cell. As I said, it's the top of a cell, but now it's looking down, like it's facing downwards. So for that, there's a nice flip tool here. At the flip rotate tools, you can just flip it upright. You can also, on the right-hand side, this one, we can flip it to the left. So these tools are just for turning the view of the data that you're looking at. You can actually apply it also in 3D. So you can flip if you click on the 3D view, you can flip it in 3D also and manually turn it. So enough of that. What I want to show you is first of all, what we are looking at. If we are clicking on the volume data object at the top right, we have all these options here. The one option I want to show you is the clipping box, so that you can easily cut open your data and get an idea of what it looks like on the inside. So there we see, I want to put these tick marks off. So there we see the inside of the cell, as if we're cutting it open virtually. On this window leveling panel, we can change the brightness of different sections. We can, I guess that's enough to show that there's anodes and cathodes, which we can see, which are all rolled up adjacent to each other. And you see also the metal casing of the battery around it and on the inner section. So that's what the data is that we're looking at. We can put off the clipping box now. That's just to get an idea. If we double click one of these 2D cross-sectional views, this is typically what you would use to make measurements. Here we have a cathode, here we have an anode, and there are some spacer materials between them. We have not enough contrast to see very easily see the difference with the spacers in between. I think there's some graphite and there's some other materials, but the anode and cathode materials are clearly visible. The scan here comes from a reasonably fast scan on a Comet Exelon FF35 system. And the reason is this is coming from a demo case that we have done to show automation. So it is possible to fully automate the scanning and analysis of cells like this one using a deep learning model and a macro and some automation tools all together. I will not go into all of that here. I will just in this video focus on showing you what you can do in Dragonfly directly. So if you have a cross section like this, you can measure the overhangs manually without making any segmentation. But before I do that, I want to show you what is possible in just inspecting and searching for defects. So if you keep your eye on the bottom left view, you have on the top right view the top, let's say the view from the top. And if you put your mouse near one of these crosshairs, you see a triangle appearing. If you hold down the left mouse button and you move it towards the outside, you can turn this view. So you can make an oblique view. And in this way, you can keep your eye on the left bottom corner and see when, as you are turning around the object, so you're getting a cylindrical cross-section around the different angles. So you can get an easy way of looking through your data. Like, let's say, for example, that seems to be an interesting feature for me. Then what I could do is I would zoom out a little bit, and I would take this crosshair and I would place it at that point and zoom in a bit to just place it more precisely at that point. And then we can see what that feature looks like in one of these other views. So it looks in both views like a little piece starting to break off from this cathode. Let me just flip the view here. And it might be something that we would like to put an annotation marker on. So let me show you how to do an annotation. There's the first annotate option is called points. So if you click on that and you hold down Control and you click in the window, it creates a point at that location, an annotation, which is giving you the XYZ location. Let's say you would like to also add this one as an annotation, and let's search for some other flaw in the data as well. So we press Escape and we put the crosshairs again in the middle, and we can continue to scroll around the axis of the cell. So I think if I remember correctly, there was a bigger piece of cathode material broken off at some position. So what you would be looking for is broken materials, cracks, missing elements which should be there, which aren't there, inclusions which shouldn't be there, and yeah, anything which is out of specification. So this is a manual task to search for areas which are faulty. Some of it can be automated, but and I will show you how the principle of that. But for now, let's say we identify this as a flaw region here. Oh, and maybe what we do need here is a better contrast. That's why we are not seeing defects that easily. We can if we click on the data and on the view, you have this window leveling that you can change the contrast of the image. So by doing this, you would be able to more easily see flaws in the areas of interest and not covering. So let's repeat what we have done before. We just take this view and again look through the data like this. So I think this might have been what I've seen before. Small section broken off there. So we click on points again, and we have to click on the point option again and add another point. So when you have a number of annotations like this, if we want to see again the first one, we click on it on the right here, right click and center view. So there we go. There we autofocus. It's auto-focusing in all views, also in the top view. So you can see where that particular feature is in all the cross-sectional views. Also in 3D, you see the dot in 3D there. So if we look at the second point, center the view, it's showing us where that is. I think in the cross-sectional view, you might have to crop the data a little bit more. So that might not be immediately visible here because it's at that location inside there. So you can make the data itself transparent, but that's not what I want to demonstrate. I just wanted to show you how to make points. Once you have made a number of points, annotations, indications, you can right click on them and you can export them to a file. So you can save them to a CSV file. Let's call it out7. And you can then go and look in that folder, and out7, I think it's just opening up, gives you the data, the XYZ location of each indication. So if we go back to Dragonfly, the second thing I want to show you is manually measuring the overhang heights. So if we look at this view, it's possible to make measurements of the overhangs manually using a ruler. The annotation panel here as a ruler. And if you now go here and you can select, you can just do this a number of times and you can make measurements. You can also adjust these measurements. So you can zoom in and you can go back to this one and say, okay, this one I want to adjust, please. I didn't draw it in the correct location. If you are interested to see the actual pixels in the image and see where your measurement is relative to that, you can go to the nearest interpolation mode. So you see the actual pixels and you can decide based on that where to draw this line actually. And so you can do different fine adjustments here. I'm going to just leave it like that for now. And my main point here is to show you how to do that. And then with these rulers, there's 5 rulers now, and they are overlapping here. So a nice little feature is to, when you click on any one ruler, you can use a floating caption option, this one here. So you can position the measurements in different places. And you can do that. You can do that. And you can do that. And you can do that. So at that point, what we can do is you can make an image. You can right click on the image and export a screenshot of that view. So you can save as a JPEG file. And of course, if you're doing this many times, you might want to save this into a CSV file. Again, the same thing. You highlight all of these. What I did was I clicked on the first one and then I'll hold down Shift and click on the last one. It highlights all at the same time. And then right click, export data to file, also a CSV file. Let's call it out8. And in this out8 file, if I open up that, it gives me 1, 2, 3, 4, 5 rulers. It gives the length of each, the XYZ location of the start and end points of each. So that's the way to make manual measurements. Of course, making manual measurements might be quite slow if you have to do all of those overhangs in a full cross section and maybe make 2 cross sections per cell. This with a number of cells per day being scanned, maybe 10 minutes per scan. This is going to take you more than 10 minutes to do this. So for this reason, making a segmentation of the overhang regions and or the anodes and cathode regions, and then making measurements automatically from those can be a better solution. Even in the normal Dragonfly, you don't need full automation. All you need is a deep learning model to define what is an overhang. And this is what I want to demonstrate to you how to achieve this. So before I demonstrate how to train a model, I want to show you how I did this to train a model in the first place, and then what the result of that model is. Let's just get let's just get everything resetted to its original layout and center the crosshairs so that we have roughly the center of the cell. So this is a cross section through the center of the cell. Let's flip it again upright, and let's take this region here for applying a deep learning model that I've trained before. So I want to demonstrate to you what is possible. And what I've done is I've trained a model, a deep learning model, to make the segmentation of just the overhang regions and only those which are actually adjacent to cathodes. So the anodes will be segmented in this deep learning model only up to where the anode adjacent to it is starting. And that's exactly what we want. We want to know the length of each overhang. So let me show you in the segmentation panel. I want to use, at the bottom is called something called Segment with AI, and I'm using a model which I've trained called Battery Overhang Segment 20th of May. And instead of segmenting the whole data, I just do a preview, which means it's segmenting only this window that we are looking at, only the slice. So it saves a bit of time, and that's all we need actually. So there we have the result from this deep learning model. So that's a very nice result. And with this yellow output, let me demonstrate to you. The output of a deep learning model is something called a multi-ROI. So there are three classes in this multi-ROI. The cathodes, the background, and the anode overhang. So the yellow one is what we are interested in. If I right click on this and I export this class as an ROI, this is what we want to analyze. So the way to do that is right click, go to new multi-ROI. So now I've got a multi-ROI for one, each overhang is one object or class in the multi-ROI, so I can calculate values for it. If I right click on that, I can compute measurements. I can compute basic measurements as always in 3D. So I can take the maximum length, which is the maximum ferrite diameter, or you can use, in this case, 2D measurements because we are looking at 2D tools. So it's a 2D segmentation. It's where I didn't click on that. Okay. So 2D measurements, I want the 2D major axis length, and I want to compute that. Close. And at the bottom here, we can show the 2D major axis length. So we can see the longest one is, or these two on the right are 1.28 millimeters. And the shortest one is the most purple one, this one it seems, which is about 1.05 millimeters. You can change the color mapping. You can change it to be, for example, blue to red. Sometimes easier to see the difference for me there. And that's basically how you make analysis with the result of a deep learning model. Now, what I would like to show you is how I trained such a model in the first place. And we do this using a tool in Dragonfly called the Segmentation Wizard. So it's a wizard which takes you through the steps of training a model in an easy way without being an AI expert. And this SegWiz object here is a previous session of this. So I'm just going to reopen this and show you what I've done before. So in this Segmentation Wizard session, there's a different window which comes up. There are different frames. Frame 1 is a selection where I have defined what is the cathode, background, and anode overhang, as you see. Frame 2 is a different region of the sample. 3 is another similar one, but wider in scope, and number 4 and frame 5. So I gave it 5 frames like this. And notice in particular, there are some additional anodes here which are not adjacent to cathode materials. And I've specifically trained the model not to segment those. So this is quite a challenging task, actually, to have only the overhangs adjacent to cathodes, where anodes and cathodes are next to each other. So the training was successful, in this case with a specific kind of model. Just to show you there, this is a monitoring frame. So this is what you will see while it's training. And this is where you look at the kind of model. And I will show you that options are available for that, because I will do the whole process from the start without going through the full training. I will just show you how to set up the training like that. But I wanted to show you this because with this setup, I got a very good result. And I won't go into that much detail for the training right now. So I will now click on exit. So I exit without publishing because I changed nothing. So that is your first introduction to the Segmentation Wizard. Now we will actually do a Segmentation Wizard session, a new one. So I click on AI, Segmentation Wizard, and new. It asks me if I want to start with already a trained model. No, I want to start without a model in this case. And what we can do is we can zoom into one region like this, and we can click the plus button. So this is now our first frame. So in this frame, we have to tell the model what is what. We can have 2 or more classes. Let's train only with 2 classes, not 3 as I had earlier. So let's make the first class let's make a simple segmentation here of anodes and everything else. So we go on the left and we use a 2D brush. So we use a full brush. The first class we can make the background. So I'm going to make a background. I'm not going to paint all pixels. I'm just making a bit of a selection like that. And the second class, I'm going to make the cathodes, anodes, and I'm going to use not a full brush, but a local Otsu brush upper. So in this case, I can just paint all the bright areas. This is everything bright under the brush. And we have to tell the model also inside of it here that these are the things that we are interested in to have also. So we have to give it some examples of what we want here. So we can do that. You don't need full segmentation. I think that'll probably be enough for a start. And then we can go somewhere else in the image, like in this region, and add a second frame. The second frame, if I click here on the mixed, I want to make this a monitoring frame so that while it's training, we can see how well our model is doing. The first one is called mixed because it uses the data for training and validation. Here it's only using for model monitoring. So we are ready to get started. We can start training. We can use either a pre-trained model or one of these model 1, 2, or 3. The model 2 here is the default one, which is used in 95% of cases. In our case, now we're going to use a pre-trained model from the Dragonfly team, which should be a bit faster than usual. It's not pre-trained on this data. It's just pre-trained on data previously exposed to CT images. So if we click on continue, it loads this model up and starts the training process. So we wait now for the training to start. Deep learning is something which does take a bit of time. It's not a fast, quick solution to see if it's maybe working better than something else. Deep learning is really useful only when you need to automate your work or when you really cannot solve the task at hand with normal methods, or if the normal methods are too manually taking a lot of human time, effort, and can be biased by a human operator getting tired. So it does take time to train a model, but once you have a good working model, you can apply it to many scans which are looking similar and have reliable results like that. While we are waiting for the training to get started, I can also explain that all model information is at the top of this picture here and saved together with the model and with the training. So everything is in there, and there's even data augmentation. So even though we gave it very little input to work with, it's already taking that and making different versions of that input data, which is helping the model to converge to a decent solution with only limited inputs. So what you see at the bottom is the progress on the first epoch, which is the first round of training. And typically you would train for at least 25 epochs. So it would, depending on the size of the data, the amount of inputs and so on, it can be from 20 minutes up to 12 hours for a training, depending on how big your computer is. And this is particularly working very strongly on a GPU capability. So we had an error. Could be that we didn't paint enough pixels because we had very few pixels of this cathode material here. So let's try to add a bit more. Let's try to solve this. Oh, I made a mistake there, so I need to hold down Shift to remove. And there we go. I think let's add a bit more. Okay, let's go again. So the segmentation wizard is interactive like that. So usually you can train a little bit. If it's not working, you can stop and add some data and continue to train the same model. And you can also add more frames as you go along. You don't immediately have to add 5 frames of input data. You can use one input frame and then use that frame or that initial model to populate a next frame and then add fix that up and continue like that. I will try to demonstrate that in this video also. Let's just see if things are starting off in a good way here. Okay, we have some action. Now what you see on the right is the preview of the first round or epoch of the training. So the deep learning model already knows pretty well what is background, and it's still getting a bit confused with um, anodes being segmented as well as cathodes. We don't actually want both segmented, so I hope the model will converge. If not, it makes a good case to show how to add data to it to fix up the knowledge of the model. Either way, what we have on the left is the loss values, which are a way of comparing the prediction to that what we gave it. So subtracting the prediction to the ground truth, or the prediction from the ground truth, should give you ideally 0 if they are identical. And these values strive towards 0. So if these values decrease from one epoch to the next, as we see there, it did, then we're going in a good direction with the training. And typically you should leave this process for at least 20 epochs because sometimes there is a bit of settling down that happens. So as you see, it takes a bit of time. It's not something that is completed in 2 or 3 minutes. I'm going to wait for 1 or 2 more epochs, and then I'm going to show you how to add data to that model. And that's basically all I want to show you today, like how to get started with training your own model to make this kind of segmentation. And important thing, once you're happy with your model, how to save it in order to use it outside of the wizard. All right, so we have still improvement, and somehow that's supposedly an improvement on the right. It's not really what I was hoping for, but let's leave it a little bit. We gave it very little input, so it might take a bit longer to converge. But my aim here was not to train a perfect model live in a video. My aim here was to show how to use the tools, and I think I've done that. I will continue to do these kind of videos for other application types, also potentially for batteries. So if you have specific requests, please let me know. I think the best way to teach how to use models is to demonstrate, teach how to use software is to demonstrate how to use it on specific data sets. I hope that is useful for you. So there we have what looks better to me on the right, but the loss values are not actually better. So it's kind of jumping up and down, and it's converging somehow. So it's quite interesting to watch sometimes, but you can also leave it and come back after a coffee or break or a lunch break, or even leaving it to run overnight, depending on your time available. And if you don't have a lot of time available, the best solution is to provide a lot of very accurate input data, defining the frames very well, and then making 5 to 10 frames, and then making a lot of data augmentation, and then leaving it to train for a long time. That's the best way to have one round of training, which gives you a robust solution. So it's still going to take some time to converge here, obviously. Let's stop this process because we didn't give it a lot of inputs. I think what we need to do here is it's being confused about what should be inside here. So what we can do here is we can take the green class and we can add more data here. We can use the full brush and we can go in here carefully and give it this kind of input so that it knows what is what here. This is all background for the kind of model that we are training. This is not necessarily the only way. This is not what my other model was all about. In my model that I've demonstrated earlier, I trained a 3-class model where the anodes and the cathodes were both segmented. Actually, the anode overhang and the cathodes and the background. So in this case, I would add more data like this and then continue to train. Let's see what happens now. And you don't have to use sparse data. You can define all pixels. You can paint all pixels in the frame. This is, of course, the best. But I just wanted to show that it's not necessary to go into all of that detail. And there's even a bit of a mistake down here. So if there's mistakes like this, where my mouse is now, this would confuse a model quite a lot because we are telling it that's what we want segmented. So our final result will have such features at the tips of the anodes, which we don't actually want. Every time it sees something like that, it would segment it as if it's an anode. So since we gave it some inputs onto the difficult regions in between the anodes, being background, where there was no info before, I'm quite confident we'll have a good solution, or a good looking solution, quite soon, actually. As I said, I'm not going to run through the full 20 epochs of training here. So we'll just have a quick look and then I'll stop this process. And I think that's it for today then. All right. That's actually a beautiful segmentation. This is what we gave it to work with. And so the segmentation is actually very good, even on the first epoch. So we actually, what I would do usually is I would now still leave it for 20 to 30 minutes, and then I would use this model. And in this way, in this case, we can make measurements of the lengths of all these anodes. All right, I'm going to stop it here. And the way to save a model, I still need to show you. So there's two ways to save it. On the model tab here, you can click on the model and you can click on the save button and publish it to your system. So it will be available in your Dragonfly system. Or you can exit and it will ask you, do you want to save it? You have to click on the button, and I want to say here, yes, I want to publish it as a, give it your own name, and click on publish the model. I'm going to exit without publishing here. And that's everything that I wanted to show you today. So I hope that is useful, and I'm going to stop this recording here. Thank you and goodbye.